calculating the pH of a weak acid is a bit more complex than it is for working out a strong acid. With a strong acid, you just have to see how many hydrogen ions can be released for 1 mole of the acid, and then you know what's the mole ratio. So if it's a 0.1 moles per litre of hydrochloric acid, for example, you know that it's going to make 0.1 moles per litre of hydronium ions when it dissolves in water, or when it's been dissolved in water. However, with weak acids, because they only partially dissociate, we don't know how much of it has actually become hydronium and how much has stayed together as the acid. Good example I've given there is ethanoic or acetic acid, and just showing that the H is going from here, so even though it's HA, sometimes the H is at the end. The reason for that is that most of our weak acids are our organic acids. So if they've got carbon, hydrogen and or carbon-carbon bonds within them, they're going to be weak acids. So that's what we mean by organic. The other things that you're going to see quite commonly when we look at salts later in the week is that it's the conjugates of weak bases as well. For example, the ammonium ion is an acidic ion, it's a weak acid. So if it's weak, it's an equilibrium. That means it has an equilibrium dissociation constant. And because it's acidic, it's a special type of dissociation constant called Ka, so the acid dissociation constant. The bigger your Ka value, the more products it will have, so the stronger the acid. So the bigger the Ka, the stronger the acid. We're looking at things with Ka values in the region of 10 to the minus 3 and lower. Okay, so they're quite small. Ka numbers seem to be a bit silly. 10 to the negative 3. They're very, very tiny numbers. So what we tend to learn to use instead is a thing called their pKa. Just like we don't remember hydronium ion concentrations for how strong or weak an acid is, we remember their pH to make an inference. We can use pKa the same way. Again, it's basically a 0 to 14 scale. It does go higher, it does go lower, but if we think of it that way, it's easier. And it's just the negative log of the Ka. So if a very small Ka is a very, very weak acid, that would lead to quite a big pKa. It's a negative log scale. So just like in pH, the higher the pH, the more alkaline or less acidic something is. The higher the pKa, the weaker an acid is. The higher the pKa, the weaker an acid is. Because it means that it's got lots of this and not much of this. Alright, so that's a relationship you need to know. Big pKa, very weak acid, which means we've got a couple of assumptions up there. Those assumptions hold true better for weaker acids than they do for stronger. I'll get to that later on. Okay, so we need to know about the relationship between these two here. An inverse log scale, just like hydronium ions with pH. As one gets bigger, the other one gets smaller. Okay, a big Ka means a stronger acid. So a small pKa is a stronger acid. Okay. Right, so once we know that it's an equilibrium system, so it's got a very large, so 3 or more pKa, then we can have a look at writing an equilibrium expression for it. And so that's this one here. And looking at the equation, we can see there's 1 mole of hydroniums for every 1 mole of A minus. Now A minus is a chemist's shorthand for the conjugate base of an acid. A minus. A for acid, it's A minus because it's lost its H plus. So this is its conjugate base. Not always alkaline in nature, but it will be in this case. Okay, so because they're in a 1-to-1 ratio, we could assume that their concentrations are the same. It's not technically true because these things are dissolved in water. And water dissociates as well to give 10 to the minus 7 moles per litre of hydronium and 10 to the minus 7 moles per litre of hydroxide. So whatever the value is for these, you'd actually have to add 10 to the minus 7 to it. That's such a tiny, tiny number. The bets are it's not going to change the concentration much at all. If I look at my answer down here, it definitely wouldn't. 10 to the minus 7 is still 3 more decimal places away. So it's not even shown there at 3 significant figures. However, when you get Ka values that are getting up around that 6, 7, 8, it does start to affect it. So you have to be aware of that assumption. Okay? But it doesn't change it by much. And not enough to change the pH, which we'll get to later. So how do I use all of this information to find, sorry, I've missed an assumption. So we've got that assumption. So effectively, this is hydronium ions constant squared. So you can rewrite this like that, because we're assuming they're the same. And they basically are. Okay? They're the same enough that this will work for finding pH to 3 significant figures. Not much more, but it will to 3. The other thing is, being weak, we know that not much of this is actually dissociated. So whatever concentration I started with, close enough to that is what I'm going to end up with after I put it in water. So I can assume that if I had a litre and I put 0.1 moles per litre, sorry, 0.1 moles into there, I'll still have that 0.1 moles in a litre. Not much of it will have dissociated, become hydronium and the conjugate. So in here I can assume that HA is going to be whatever the question says. So it's a really good habit to get into having a highlighter or a pen for underlining key information. One of them is the pKa. You need to turn that pKa into a Ka value because you're going to have a Ka expression. Another one is for you to underline the concentration of the acid to start with, because that's not going to change. That's going to go into this equation as well. And you'll rewrite this top bit as hydronium squared, because you've made that assumption, which usually will be true. So let's have a look at this example here. I've got 0.100 moles per litre of ethanoic acid, and I'm given a pKa of 4.76. I hope that's correct. I didn't look that one up actually. So there are a couple of steps to do. My first step would be to write the balanced equation. Then from the balanced equation, I would write my Ka expression. So those would be my first two steps. I would then rewrite my Ka expression with numbers where I can put them in. Now, I'm not a mathematician, so I don't care if I write something down that's not correct mathematically. So when I see that it says that Ka is 10 to the negative pKa, I'm going to leave that as 10 to the power of negative 4.76, and I'm going to put it there like that, because I know how to put it in my calculator like that, and that's all that matters. The pure mathematicians are having a small cry in their beds tonight because I'm writing it that way, but that's too bad. I don't want to make errors by rounding it off too early. So I'm still going to use that as that number in my calculation. Then I've got my hydronium squared, as I say, which I've taken from there, and that 0.1 I'm transferring into here. Well, now I've only got one unknown. So I can rewrite this as hydronium equals the square root of the Ka times the acid concentration. So if you wanted a general equation for this, that's it there. So if you're better at learning an equation rather than applying some rules, learn that off by heart. For a weak acid, it's only true for a weak acid or an acidic salt. Okay. So once I do that, I get 1.32 times 10 to the negative 3. It's a concentration, so make sure I've got my units. I then plug that into my pH calculation, negative log hydronium ions, and I get 2.88. 3 significant figures because this is 1.00, and also because my pKa was given to 3 significant figures. Okay, I've got that data to 3 significant figures, so my final answer has to be as well. Okay, I want to address the assumptions, particularly this one. In this case, this assumption is incorrect. It's actually incorrect. So I want to address that, because if you're going to make assumptions, you want them to be correct. In this case, it's not. If this number, 1.32 times 10 to the negative 3, was written as a 0 point something or other, it would be 0.00132. That means this third significant figure is going to be altered. And so I'd actually get a new concentration. If this much is reacted, then that's got to be 0.1 minus this number here, because that's how much did react to make the conjugate acid, the conjugate base and the H3O+. So I know this number's wrong. So what I've done is I've shown you what would happen if I use the numbers. So first of all, I've got my HA, so my acid, and I've got my H3O plus, which is what's being formed from it. So if I go that minus that, that tells me how much HA is left over. So that's initial, and that's final. So at the end. So therefore, that number would have to go into my calculations instead of 0.1, because they're not the same number. They're different. So I plug it into my equation, and I get 1.31 times 10 to the negative 3. Let's just check. Yeah, that's basically the same number as that. It's not identical, but it's basically the same. So I do my pH calculation on that, negative log of this number, and I get 2.88. Now, if I go back to what the question probably would have been asking, which is what is the pH, I've got the same number. So even though my assumption was subtly incorrect, it's not going to matter. That assumption still works. Now, you're not going to get many acids that are stronger than ethanoic acid, or many concentrations that are more out by this one. So if it works for that one, it's going to work every time. So that assumption is going to be fine, so long as it's a weak acid. Any questions before I turn that off?